Hey, what's going on, guys? WukongJS here. I've just implemented search function within my CNC engine. So in this video, I will try to quickly cover how the search function actually works in general. So I'm using negamax search with the alphabetical pruning. So that's kind of the name of the algorithm. It works exactly the same way as it does in my international Western chess engine WukongJS. So literally the same stuff, just bearing in mind that the number of pieces in CNC is a little bit different and the number of words is different as well. I needed to make a couple of minor tweaks to just fit the move ordering, and that's literally it. All the rest of stuff works absolutely the same because alphabet search is kind of like a chess variant agnostic stuff. So that's I've been covering that in the previous series, so nothing really new here to say. So I've used almost all the basic alphabet search optimization techniques, and I try to implement them in the most simplest way possible. So we even do have a transposition table with a variable hash. So later on it would be possible to, hopefully, if I ever manage to connect it to GUI, that would be possible to set up the hash. I didn't yet try that, but well, we'll see how it works. There are some issues arising regarding the communication protocol, so I can't yet get a clear picture of how the so-called UCCI Universal Chinese Chess Interface protocol how it works. I mean, I understand how it works. It works just like UCI, the standard Universal Chess Interface, but it has some different names for the commands. So nothing really special, but without a clear idea of how that works, it's impossible to connect to the GUI. Also, I have an issue with the GUI itself because I've been testing all my engines within the Arena GUI, but unfortunately it doesn't support Chinese chess. And the Windboard, the one that does support, it doesn't have those features that Arena has, so I can't really see what the particular interaction between the GUI and the engine, which is also weird. So that would be a little bit blindfold work, but still I hope that eventually I will be able to connect the engine just to see how the search behaves in the actual game versus itself, like this engine versus itself, playing itself, and versus some other engines. Well, at very least against Max G, but by Harmgert Muller. It would be incredibly exciting to have a look at the game, because I have no idea how it comes, but anyway. So I've managed to count to depth of 10. Well, it's a little bit time consuming, so it goes for about 10 seconds maybe for depth 9 and around 20 seconds for depth 10, maybe even a little bit more. So I just want to make sure. Well, I will demonstrate the depth 8 because my video recording software is now working. So just to give you an estimate idea, just to give you a rough estimate of the performance of this engine. Well, bearing in mind this is written in JavaScript, I think this is not really that bad at all. So it's already going to depth 8, yeah, and we are outputting the best move. So let's have a look at the principal variation line. So I personally like this one at depth 7. So we have h2 goes to e2, which is the standard book move, if I'm not mistaken. h9 goes to g7. So h9 goes to g7. Knight covers, protects the pawn. Okay, reasonable so far. b2 goes to c2. So this bishop, this cannon goes here. Well, a little bit controversial because maybe knight would go, or it goes, say, here on d3, and then knight goes to make cannons support each other. But these are the chess engines. They are thinking a little bit different than us humans, so not a big deal. I think this is quite pretty engine style here. So I think that might be just the case. Okay, what else? So how the game goes here, b2, c2, b7, e7. So from b7 to e7, yeah, centralizing the cannons. Well, it seems to be reasonable principal variation line so far. So b7, e7, h0 to g2. Yeah, so h0 going to g2. So knight holds the center. I'm wondering, what about the pawn moves? h7, h3, g3, g4. So h7, 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 h3. Whoa, this is interesting. And g3, g4 protecting the pawn. Well, interesting variation anyway. Yeah, it's a little bit tricky to me to understand this, but at very least it doesn't seem to be a garbage. Well, probably I don't know CNC well enough, but this seems to be a pretty reasonable line. At very least it shouldn't be blundering pieces and trying to do at least something basically. So this is it regarding the demonstration, guys, and I don't know if I really should to go and explain how the search actually works. Well, the amount of code that has been added might have seemed a little bit overwhelming. So all you see now on your screen is the search. So here is the main function negamax search, which actually does all the job. Okay. Search position is a driver that is called to make this iterative deepening that has been shown here within the console. So iterative deepening happens right over here. So instead of hitting the depth directly, we're just iterating over to initialize the hash table to make use of principal variation move. So hash move and PV move are both getting sorted later on. And again, like move sorting, move ordering is the most crucial thing about Alphabetical search, because the better move ordering we have, the faster beta cutoff occurs. The less nodes would be we would need to traverse. The faster we have the principal variation line basically, and the stronger our engine will be playing at the very end. Also, it already has this UCI format output. I don't know if UCCI supports somewhat a bit different, then I would need to alter this. So I didn't really change much here. So also it deals with the GUI score, which I called in my previous engine like UCI score. So again, like this only works if the browser is active, and in case if there is another variable, if there is another JavaScript file responsible for the GUI. So this is already some sort of an interaction with the GUI to update the GUI variables and later on display on the web page itself. So that's it. Also, sorry guys, within the init all, we just added this init hash table. Again, a hash table has a variable name, has a variable size from, I guess, 16 to 128 megabytes. Yeah, I didn't yet specify that. That would be specified within the UCI protocol itself. I just remember this from my previous implementation. Also, we have a quiescent search serving the purpose of getting rid of the horizon effect. So just literally to avoid engine dropping pieces when it exhausts the depth basically. Here is the quiescent search. Also timing is implemented, so I didn't yet test that, but that should be working because I didn't really change much there. So yeah, the routine to store the principal variation move. Okay, sorting routine. Yeah, so lots of stuff really. So like probably a big book can be written on the Alphabetical search itself. So I just wanted to prove the concept that, well, I've updated the MVVLV table. So most valuable victim, least valuable attacker, which is the core table to score the moves. So the idea is that the moves where pawn captures queen, or sorry, pawn captures rook, or to be exact, if pawn captures king, even though pawn does not capture king, but still, this move would be sorted first, and then the move where, say, rook captures pawn, that would be the very last move to have a look at, to search for, basically. So quite pretty simple stuff there. An interesting tweak with the generate captures. So I've slightly decreased the speed of the move generator by given one extra condition, but this saved really lots of code. So I think for didactic approach, this is quite pretty not that bad, especially bearing in mind that we still would be hitting around 6 or 7 or 8 even plies in Blitz. So I think that's just really not that bad for the JavaScript engine. And again, like bearing in mind the fact that the main purpose of it is to play versus humans in the GUI, I think this is just good enough search. So yeah, I didn't yet try to play versus this engine because there is no interface at the moment, but I strongly believe that it will crush me quite pretty quick. I would only need to make sure that the mating possibilities are working nicely. So that's kind of one of the interesting questions to consider. But otherwise, it should be just fine. So I have the very basic implementation of the hash table. So nothing really new here. Yeah, and evaluation has been covered in the previous part. Okay guys, so I think this is it. So we're really coming to the very first initial release. Again, like I'm sorry for I'm not covering all this tiny little details, but again, like what I did, I literally copy pasted my own search from my own engine, but from the International Western Chess. So again, like so the things that I've fixed here is miserable, so nothing really much to talk about. So you can just use the search to learn how it works. Not the best ever example, but hopefully quite pretty clean. So this should be, yeah. So in questions we're generating only captures, yeah, and in negamax search we are generating well, where is that? Oh, where is the generate moves? Should be there. Oh, where is the generate moves? Come on. Okay, here they are. Generate all moves. And within the push move, so let me just go to the push move. Now within the push move, what we do, so we are pushing only if the move is available, basically, and we are adding this quiet move, non-capture moves only in case if only captures is equal to 0. So we I've added extra flag to push moves. So now within the generate moves, it takes this only captures and sends this only captures as one additional argument every time we're trying to push the move. So that's kind of how it works. Nothing much. So well, probably the very last thing I can do is just to highlight all those basic search optimization techniques being involved here. So yeah, but obviously I've changed this to generate to all moves here in the perf as well. So it's likely to be a real engine at the moment. So it searches, it does all the stuff. So apart from the GUI and the interface, this should be already a full-blown engine to play the game of CNC with. So I think this is quite pretty cool. Again, I really can't say much before testing it versus other engines, and at least try to play a couple of games to see how fast it would checkmate me. So without that, it's hard to measure. So maybe I just missed something. I don't know. Everything is possible, obviously, but generally this seems to be quite pretty nice. So first we read the hash table. If we do have a hash mode, that we just return score directly. If we don't, then at very least we can use the best move. We're passing the pointer to the best move, and then we would be then we would be ordering this move first, just to increase the probability of beta cutoffs. Every 2047 nodes we check whether we still have time or not. If we don't, we just return 0, so just drop the search and return the best principal variation so far, and the first move from that is done down below in the search position function. This line is quite pretty. I can't pronounce the pretty word. This is quite a pretty essential line here. So, but hold on a sec. I just thought. So the idea is that the threefold repetition is a draw. So I think I need to add an extra parameter here. Sorry guys, just I think I need to do like if 60 in this case, not 100 but 120. So 60 moves, 120 plies. So see, like I've just found a minor bug here. Then we want to return 0. So if I'm not mistaken, the 60 rule moves means a 0 in CNC, so that's quite pretty fine, just like in international Western chess. But there is an issue with this is repetition. So whenever we face a threefold repetition, if this is the perpetual check or trying to attack a piece, well, literally this implementation gives a penalty for threefold repetitions. So the idea is to avoid going for threefold repetitions, because this would be treated as your material down of the score of canon is used as the margin, as the evaluation margin. So let's say the sided move is better and it's trying to force the repetition. So in this case, it would have a score like it dropped a couple of pieces. Well, maybe let's say not a couple. Let's say if we do have an equal material and the side that is slightly better is going for threefold repetition. So if he persists, he just loses the entire game, which is so weird. So he gets the score of as if he was losing a cannon. So he treats the threefold repetition as losing material. Hence, he won't be going for that variation. Well, hopefully, in theory, at the very least, this is how Harmgert Miller does handling of this repetition within his Max Chi CNC engine, which is the minimalist, very tricky, interesting, and tight engine I'm gonna be trying to play with my engine. So that's it. At the depth of 0, we're obviously returning the quiescent score to make sure that we're not suffering from the horizon effect as been explained before. Mate distance pruning doesn't do much. A part of abandoning search if he already found a mate. So let's say he found a mate in 2, then he just immediately drops. He's no longer searching for a given amount of time. Let's say he has like 5 seconds, but he'll just find a mate in 2, so he's not going to be searching after he found a mate. He just returns immediately. Or if he say have the depth of 10 and he found a mate in 2, he would just return directly without searching the entire depth, because the object of game has been reached, the mate is there. It's not affecting the plane strength only, it's just within the GUIs. It just goes very quickly when he sees the mating sequence and when the scores are mating scores. That's a very simple thing. So what else? So in case if we have a situation where a king has been exposed into a check, I'm just wondering, is this correct? if our king has been exposed into a check by the opponent, in this case we want to search deeper because in order to avoid getting mated with a forcing sequence. Well, at very least this works like a charm in international Western chess. I'm not sure how well this would be working in Xiangqi, so just hard to see without a testing. So if we are in check, we're just increasing the depth. This is known as the search extension. I have the only extension in my search, only this check extension. Then we are entering a territory of search optimizations before the actual search begins. So all these techniques are about to come only if at very least two conditions are fine. So if we're not in check, so if we are in check, we're not going to be doing all of this tweaks to optimize the search, because we instead want not to miss any opportunity and would be searching much deeper if we are in check. Also the same if we are in the principal variation node. For those of you who's not aware of the name for nodes within the Alphabetical search, let me just quickly explain that. So we have exactly 3 types of nodes in Alphabetical search. So we have nodes that we have the principal variation nodes. It occurs well, in this particular case, I'm using a little hack to get the principal variation node, using this tweak with evaluations. But actually, the true principal variation node occurs. Let me just find this place. Occurs here. So this is the core of Alphabetical pruning. So we have 2 main situations. So if score, after we search the score, if it's better than alpha, so alpha is the score for the site to maximize the score, and beta is the score for the site to minimize the score. So in case of score is, so alpha might be treated as a best score in negamax brute search. So I hope that's clear. So if the score is greater than alpha, well, a part of setting up the hash flag, which is a long story to explain, so here is the territory when we have a so-called principal variation node. So whatever we want to do with the principal variation node happens here. And in this part where score is also not only greater than alpha, but also greater or equals than beta. So let's say here we have alpha. So here we have alpha, and here we have beta, and we coming from this side. So this is alpha. So we're coming, okay, alpha. So greater than alpha, then we proceed. And now we are within the alpha and beta. So here is beta, coming to beta. So if it's also greater or equals beta, then we just return the beta, because this is known as the so-called fail high node. So all this Alphabetical search optimization techniques, they all are about dealing with this alpha beta window. So like 2 margins. And again, like this particular implementation uses so-called fail hard framework. Which means that the best score can go beyond the alpha beta bounds. So we always are within the alpha beta bounds. That's why the maiden score is not infinity, like in fail sub frameworks, but it's less than infinity, to make sure that we have to make sure that we're not going to be exhausting the depth, that we're not going to be exhausting the infinity score. Okay, so what else? So here we have every time this condition fires, we have the node, so-called principal variation node. So this is the best move found so far. Okay. Here we have so-called fail high node, and here we have so-called fail low node. So all the optimizations, they are trying to deal with these 3 types of nodes. So the first class of optimizations, we want to no matter how we get this principal PV moves, principal variation moves, well, most likely if we don't have a hash table, we can just store this principal variation move. If we do have a hash table, it's actually literally enough only to use best moves from the hash table. But my engine contains both approaches, just for make it more clear from the didactic purposes perspective. So if you have a look precisely at the source code, you will notice that at the move sorting. So I'm sorting both principal variation move and also the hash table move. So what else? So this is one major part of the search that can be optimized. So wherever we have this principal variation score, we can order that move appropriately, and that would be improving the move ordering significantly. And the more precise move ordering is, the less effort it takes to actually do the same job, but in the less time-consuming manner. Okay, so the next part to optimize is fail high nodes, and this is the territory of so-called null move pruning, and we'll come to that. So null move pruning makes beta cutoffs occurring earlier, like before the search. So there is an interesting trick to do that. We just switching the side, making so-called null moves. So we're just not doing a move, but switching the side, and asking opponent to make one extra move. And if the score is appropriate, then we return beta instantly without searching deeper. So that's how the null move works. But again, like there is lots of theory, and the matter of how strong your chess engine is, how deeply it searches, how accurately it searches. It's all the matter of how deeply you understand this basic concepts of the alphabet search. So I have a very basic understanding. That's why my search actually sucks. So what I achieve here is not really that great, but I think for those purposes, I'm going to be using this engine. This is literally enough, because for plain versus beginner humans, it's more than enough, really. And the very last part of the alphabet search here were so-called fail low nodes happening. So fail low nodes are those nodes where alpha has not been increased during the search. That happens, yeah. In this case, we also have a very powerful tool to actually optimize the search, and that is called late move reduction. So we're searching those moves that are not increasing alpha, so they are not very likely to become principal variation moves in future. So we're searching them with a reduced depth. And again, like the level of difficulty of the level of complexity of late move reduction varies from one engine to another. So the stronger engine we have, the more sophisticated formula is used, and not only one formula, lots of conditions are used to make that late move reduction. So with this idea in mind of the core places within the alphabet search to optimize, we can now quickly run through these very basic optimization techniques. So let's at very least try to name them. So we start with getting the static evaluation, and this would be used in several places before, in evaluation pruning and in so-called razoring, in order to return the score without even searching, only based on the evaluation. So the idea is that if we are good, just simply saying, if we're good enough, then we can just return the static evaluation. That's kind of the core idea. So if you walk a little bit deeper within the source code, so we doing this only if depth is less equals than 3. We make sure that that we're not dealing with the maiden scores potentially. So up to it's not at least not made in 100 moves. So if it's not the case, then we go in further on. So calculating the evaluation margin. So the margin is variable. It's the better you tune in, the more the better search you will have. I'm using just the weight of the red pawn multiplied by the depth. So that's one of the simplest way of calculating this sort of a thing. And if it happens that the statistical evaluation minus this margin is still greater or equals than beta, then we just return this evaluation, return statistical evaluation minus evaluation margin. So that's sort of a hack here. Okay, so null move well, actually evaluation pruning is also known as the static null move pruning. Now null move pruning takes this sort of a concept to the new level, but instead of just doing this based on the evaluation, it actually, so make null move and take null move. Well, probably I could have shown you this. It's nothing really complicated there. So make null move. We just backing up the current board state, reset in the, oh man, it's not 50, it's called 60, another bug. 60. Yeah, it's good to reveal the code. 60 rule move counter. So we store in this, resetting the 60 rule move counter, and literally just changing the site, that's it. Very simple. Well, hashing the site to make sure the hash keys are fine. And then we're running the search. We'll now come back there to null move pruning to make sure how it works. And then when we take the null move, we literally just restore the board state from the stack. So restoring the site, restoring this 60, oh man, not 50, 60, save, 60 here, okay. Yeah, or otherwise it would be disastrous. Just wanna, oh, sorry, save. Just wanna make sure that there is no more 50. Okay, in my code. Make null move. I hope this is still searching. Yeah, hopefully. Okay, so literally make null move makes to switch the site and let the search run again. But here we're not going for depth -1, but we're going for depth -1 and minus some constant. So someone used -2, someone used -3. This measures how aggressive the null move pruning is. It's really arguable which one to use. It's really all the matter of the experience. I'm not that good in all the search optimization techniques to discuss this with you guys. I just use the most standard -2. That's it. Also, we need to make sure that we're not making null move 2 times in the row, which was one of my mistakes. So we use do null in every other place but this one. But if we do this null move pruning, we need to make sure that the next one won't be like that, because well, I had an experience in my BBC chess engine. I wasn't doing this, and that was working fine even without that. But still, sometimes this might be leading to positions where engine starts losing material with no clear reason why. So better not to make a null move 2 times or more than 2 times, or even more than 2 times in the row. And then again, like very simple stuff. So we get the score that is greater or equals than beta. We just return beta without ever searching any move. So that's how the null move pruning works. Just a static evaluation pruning, but made dynamically. So that gives a little bit more precise results, because here we only use the static evaluation, while here we implicitly using the quiescence, because when we come to this score again, when we come to the negamax again, when the depth would be exhausted, this comes quite pretty fast, quite pretty quickly. Then we just call the quiescence, and already we would be dealing with the quiescence score, not with just the bare static evaluation. So these results are a little bit more precise. That's it. Razor in. So again, like we're taking the score, like we're taking the static evaluation that has been pre-calculated already, adding this margin. It's almost the same like we did here, but we're not multiplying by depth. And now, if already score is less than beta, and we have the depth equal to 1, then instead of searching this step, we just returning the quiescence value in case if it's greater than the score obtained by this addition. Otherwise, we're adding another literally kind of here. So here we add one pawn, and if we ever to come here, so if it's not the depth 1, then we just add in another pawn, and only in the cases if the score is less than beta again, like, and the depth is less than 4, again, like we just we just getting the quiescence result, and exactly the same steps. So we just return quiescence score instead of searching the entire instead of going for the entire search. So this is razoring, so using quiescence scores instead of searching if circumstances allows us doing that. Futility pruning lets us to not to search some moves, which also speeds up speeds the search a little bit. So first here we define the futility margins for different depths, if I'm not mistaken, right? So here I have the value of red pawn, of red knight, and red cannon. So all these values should be correlating with actual values you're using within your evaluation. Otherwise, this doesn't really make much sense. And again, like the better correlation we have with these numbers within the search, and the better they correlate with the actual evaluation constants, the stronger engine plays at the very end. So now the condition to set up the futility pruning flag. So if depth is depth is less than 4, if the absolute value of alpha is less than mating score, so make sure that we're not in the mating territory, and if the static evaluation plus futility margin, so this this list array indexed by the depth, so less than 4, so depth might be 0, 1, 2, 3, so 0, 1, 2, 3, whatever depth will have the specific evaluation margin. Here it's called futility margin, so it's the same idea, all the ideas are the same, just the implementation is slightly bit different. So in this case we just need to make sure that the static evaluation that we calculated a long time ago before plus the particular futility margin is less equals than alpha, which means that this node is most likely to fail low, basically. In this case, we're turning this futility pruning, so this means like those moves that have a very little probability to increase the value of alpha, we can assume that they are bad enough so we can drop them. But how exactly this happens, it comes a little bit later on. So if we didn't yet return from the search until now, in this case we need to move search would be later used for late move reduction, so to consider late move reduction only when the certain amount of nodes of moves has been already searched, so this is just a counter. So now we finally started generating our moves, all the moves, because this is not a quiescence, we need all the moves to search. A sorting principle variation, so this move list contains the actual moves, then we need to sort these moves. So in the MVV, LVA order, history, heuristic, killer, heuristic, so it takes just ages to describe all of them. And then we'll start, sorry guys, sorted in PV move, not this move list is sorted here. Sorted in PV move, so what is the PV move? So let's say here, we know that the previous best move was H2 to C2, so we score it first. So the next move we would be searching one ply deeper would be this one, and every time we hit this node, we just use the previous and search it first. It's not always so. In this case, they are the same, but let's say this move was then abandoned and replaced by this one. So, but generally, this principal variation move ordering helps to improve the move ordering in general quite pretty significantly. Let's say Max G and Micromax by Harmgert Müller only using this principal variation move ordering. It doesn't use any other move ordering, believe it or not, and still searches fantastically deep, assuming that it doesn't have any move ordering at all, apart from this principal variation move ordering. But it also uses so-called internal iterative deepening, which is a little bit beyond my understanding. I mean, like, I understand the principle, how it works, but the implementation is still quite pretty vague for me at the moment. But we don't really need that here. We could have implemented this as well, but okay, just forget that. So sorting the moves on the fly, this just we could have sorted moves before looping over the moves, but here, as far as the sorting algorithm itself, just sorting moves one by one, it might happen that we sort the next move, and then this next move just produces the beta cutoff, and we no longer need to sort any other moves. So that's the sorting moves here allows us to escape the search faster without doing some redundancy job on sorting all the moves when we know that, let's say, the second would cause the beta cutoff and we're done. So extracting the move. So move list index by the count and the move. We have the move and the score there, you remember. So if it doesn't expose keying into a check, then we continue. Otherwise, we just go not making this move. Legal moves counter is used for detecting the checkmate. So if there are no legal moves, then we're in the checkmate and game over. And now finally we're coming to the futility pruning. So first we're checking for our futility pruning flag that has been defined a few lines above. Then we need to make that at very least one move has been searched. Then we need to make sure that this move is not a capture. And then we need to make sure that our king, hold on a sec. Sorry, in this case, this is not our king, this is the opponent king. We need to make sure that the opponent's king has not been exposed into a check. So let's say it's our turn, we made a move, we check opponent's king. In this case, we're not using futility pruning, that's kind of it. So, and if all of these conditions are fine, we're just not searching that move. Very simple. That's the futility pruning. We just take back and we continue. That's it. We're not searching. That's very simple but yet effective technique, futility pruning. So those move futile, we're just not searching them. That's kind of it. And next, so the next, this is one of the most essential calls, recursive calls of negamax. So if we have move search equals to 0, so we enter here initially at the search. So we just didn't search anything yet. So let's say we came here, just calling our negamax initially. We're doing the null move, obviously. And here we're coming into the late move reduction territory. So lots of conditions here. So we need to make sure that we're not in the principal variation node. We need to make sure that we've searched at very least 3 moves. You remember the counter was up about there. We need to make sure that the depth is greater or equals than 2. Again, like these variables can be calculated dynamically. The more precisely they are calculated, the better potentially better results this late move reduction can bring to us. This is a very powerful technique if you're smart enough to use it. It's not my case, so I'm using the very basic one. So if we're not in check, if we're not dealing with the killer moves, not the first killer move and not the second killer move, okay? And if this move is not a capture, then we're going for this late move reduction. This is the call. So minor tweaks with alpha beta window. So instead of using minus alpha minus beta, we're kind of narrowing the alpha beta window as much as we can. So it's literally like only one point wide. So we have minus alpha and minus alpha here. So only 1.1. So let's say alpha would be like 20 and beta would be 29. So this is the very narrow window, not minus infinity and plus infinity, but let's say alpha is 20 and beta is 21. So these are the margins. These are the bounds of alpha beta window in case of recursive call when we are within the late move reduction territory. This trick helps to make sure that the value for alpha has been restored after all of this stuff being done. And then we're going for a principal variation search. Again, like you see, the call is very similar, but within the late move reduction, we're doing depth -2. Again, like this depth might be also variable. So by increasing this number, your search would be searching deeper, but potentially it might be losing some. It might be missing some winning opportunities. So the matter of making search, you might have heard the term of aggressive late move reduction or aggressive null move pruning. It's all the matter of calculating the how likely we would how much we would be reducing the depth during this recursive call. And again, like really complicated formulas exist to calculate that value, but I just really try to stick to the simplest implementation possible. So I just didn't get bothered with that, and I just have a static value here. So principal variation is very similar, but we're not doing depth -2, we're just doing depth -1, but the idea of almost closed alphabetical window is still the same. And now if it happens that during the principal variation search, just a few words regarding the idea behind the principal variation search. It simply says like, if we already have a good enough move, then most likely we won't have a better move. That's very simple logic. So let's say we have a good move and we think that this is good enough and we don't really need to search other moves. So in this case, we're narrowing this window again, like, and making this recursive call. But if it happens that there would be a move that hits exactly into this little tiny window, this single point, this is very not likely to occur, but this might happen. So in that case, we just make a normal search to make sure. If this condition occurs, if we hit in exactly this little window, this means that actually among those moves that were initially treated to be bad moves and not having a potential of raising the value of alpha, so it means like we were wrong, and actually there is a move that is capable of increasing the potential of alpha. So just like score is greater than alpha actually, so it does increase the alpha. In this case, we need to research it with the normal conditions to probably reveal the next move that would be actually increasing alpha even more compared to the current one. So again, like this all has been tested on practice through the decades basically, and I didn't obviously invent all of these techniques, and I don't really have that great understanding of how they work in great detail. So what I'm sharing here with you guys is just a very general noob's understanding of how alphabetical search works. So then finally, eventually, we're taking the move back. This means that one make move take back session has finished, and we can increment the search moves counter. And then we're coming to the heart of alphabetical search, as I was describing this already. So if score is greater or equals than alpha, we just changing the hash flag, updating the best move, increasing the alpha. This is the core line. It can work without this. It can work without this. In theory, we cannot store the PV, but if we're not updating the value of alpha, the search won't be working. So this line is absolutely essential. And here we store history moves. So if move is not a capture, then the move that has increased the value of alpha is about to be sorted as the first move of non-captures in the next iteration. And the move that has caused the beta cutoff, called the killer move, and the killer move is written to so-called killer table in case if again like we're not within the capture territory. So first we sort the first killer move, then the second killer move, and then the history move. That's the order. So first we would like to, in the next iteration, would like to search those moves that has caused the beta cutoff in the previous one. The first that caused the beta cutoff, then the second that caused the beta cutoff, and then after that we would be going for history moves. well, some engines also using b-square tables in order to for move ordering purposes, but I didn't have successful experience with that, so probably it's not an option for me, and it's rarely occurring nowadays. So one last tiny little difference compared to international Western chess. So if we don't have legal moves in international Western chess, we have if king in check, then return this maiden value. Otherwise, return draw, which means return 0, which means a draw. But in Xiangqi, if opponent doesn't have legal moves, this means that he lost the game. So we're returning the maiden score. So either checkmate or stalemate, we still kind of win. So this would be like applies, not obviously applies to mate, but applies to stalemate as well. But stalemate again, like, is just considered to be a mate. So that's kind of it. Writing hash table, well, to be honest, I feel a little bit tired already, but okay, let me just very quickly walk through how the transposition table in its simplest possible implementation works. So we have let's go to transposition table just to give a very quick understanding. So we have 3 types of scores to be stored within our transposition table. So number of entries correlating with the number of megabytes, the value to return if no hash entry has found. This doesn't matter really, it's trivial. So we have 3 flags. So hash exact means the exact score returned by the quiescence after all the stuff, and also alpha score and beta score. And well, just to here we just setting the size of hash table by changing these hash entries using this formula. Initializing table, literally just initializing this hash table array by just indexing this by the index and making all the values equal to 0. Read and write hash entry are 2 core functions to work with a hash table. So it's quite pretty simple. So let's start with the write hash entry. It would be occurring more times. So we're taking the score, the best move, pointer to the best move, current depth, and hash flag, one of these three flags. So just trying to, okay, let's just go how it flows. So usually if we do have, usually people use unsigned integers and not 32-bit like I do here, but that's the limitation of JavaScript, and then didn't really want getting bothered with hash high and hash low. So having hash bits being stored within 2 variables, that's a little bit too complicated and not good idea for didactic purposes in my personal opinion. So I decided to use only the 32-bit one. It might be leading to hash collisions in future, which results like from time to time engine might be making some weird moves, but we still I can live with that. So for the purposes I'm using this engine for, this is not a big deal really. So this modulo operation allows to obtain the index within the hash table using the hash entry as the key to get the proper entry. But this is negative. This might be negative because it's not unsigned. So we bitwise ended with this mask, which literally strips the negative byte, the 32nd bit, the 32nd bit from the hash key, and then we using it to actually modulo by the resulting value modulo by with the number of hash entries. 2 most mysterious lines of code that I don't yet understand. I've been explaining them on TalkChess. The rough idea that we just need to adjust the meeting scores in order to just can't explain this. So we are somehow adjusting the maiden scores. Just reading these 2 lines of code for me. I'm reusing them every time since then, so can't really explain. The idea is that the distance from the root node to the maiden ply might not always be okay, and then we need somehow to adjust this. So I'm sorry, I have a very vague, well, I don't have understanding of that, so I'm not going to be explaining that. But without this, it might have troubles with getting the maiden. It might have troubles with storing and reading maiden scores into the hash table. So that's why these two lines are important here and here as well when we're reading exactly the same stuff as them. So, and now to write the hash entry. So it's literally an object that we're writing at this specific index of the hash table that is obtained using this hash key. That's it. That's why we needed to generate an incremental update at this hash key. So the first reason to detect the repetitions. Well, I didn't show you that, but you just have a look at the code. Nothing special. There's just storing all the history moves, game history applies within the repetition table, and if position occurs more than once, then the repetition is returned, and that's how we detect those repetitions. So nothing really complicated there. So within the hash entry, we're writing the hash key because it's not enough to hit the specific index using this formula. Sometimes it might happen that the actual hash key available at the current hash entry might not match the actual hash key. So so in order to make sure that it does match, we store hash key explicitly. Then we store in the score. Then a hash flag, which means so this might be either the exact score, alpha score, or beta score. Then we store in the depth and the best move. And this is so-called always replace schema. So I'm rewriting the entry regardless of whatever conditions. This is the most poor way to, this is kind of like a poor man's transposition table, but it's quite pretty simple to understand, and it's really good for didactic purposes for beginners like me. Yeah, so I personally consider this way of dealing with hash tables quite pretty fitting my, well, I think that's just good enough. And then the read hash entry does all the same, but we just can obtain the hash entry, then make sure that the hash key of a current given hash entry matches the actual hash key we have now within our research. Make sure that the depth is greater or equals than the current depth. So this is another condition to like over safety condition, let's say. And we just get in the score from the hash table, dealing with the maiden scores, and depending on flag, we return either score or alpha or beta, and also we're taking the best move pointer, and we're initializing this best move with the best move we have in the transposition table. So later on, this best move getting sorted by the sort is getting sorted first. To improve the move ordering even more, because move ordering is literally our everything within the alphabet search. And if all this stuff doesn't fire, we just return the no hash constant, which means that hash table failed and we really need to search from scratch. So now the very last thing I would like to cover is where exactly the hash is being written, and where to read the hash and where to write the hash. Well, also, while clearing the search, just all the variables that we're dealing with need to be cleared, otherwise just disaster gonna happen. So timing repetitions I've been mentioning, so just looping over repetition table. If we have the application, then return true, otherwise return 0. Okay, so negamax search. So one of the first things to do before anything else, we're probing the principal variation table. So conditions, the search ply should be at least 1, so it's not the root ply. Trying to get the score and calling this hash entry. So if it's not equal to no hash in this case, and also if we're not within the principal variation node, in this case we just can return score without going down here, without searching anything. So just using the value that has been previously stored by the previous search. So the idea behind the transposition table is very simple. So if we do hit what I call transposition, so if we do hit the position that has been already searched, so we already know either exact score or alpha score or beta score for that sort of a position, no need to search it again. So the overall idea behind the transposition table is just not to do the job twice or many times. In case of engines, this might be really many times. So we read only here, reading hash table at the very beginning of the search, literally here. And now where do we write this? Where do we write? So we write, so by default, we're setting hash flag to hash alpha. So if we don't find a principal variation move, a PV move, then we will find ourselves down below here. And this is, as I've been already explaining, this is so-called a place within the alphabetical search when the node fails low. So in this case, hash flag equals alpha. So we just store in this alpha, so it's not a principal variation move, just an alpha, and we write in this hash entry. And another thing that might happen if the score is actually gets better, so we're not writing hash here, we're just changing the hash flag to hash exact. And when we come here, the hash flag already would be the value of hash exact. So in this case, we would be writing not the alpha score, but the exact score. So that's the difference. And yeah, because otherwise we just miss the better score. That's it. So if we just have a better score, we just need to make sure that the flag is adjusted appropriately and write that score. And the second place where we do write is when the beta occurs. And here we're using this hash beta flag because this is the beta score, and writing it right over here. So literally the first place where the node fails high, the second place where the node fails low, and in case of the principal variation move, we're just changing the flag, and in this case we're storing the score, but the flag would be already, it's the same alpha score, but the flag is different. So the score is the same in both cases, but it's just a matter of what the flag is used. Either this is the fail low score, which is not likely to be considered, or if this is the principal variation move score, which is likely to be considered. So that's a pretty important thing. Okay, guys. Sorry, I feel a little bit tired. It's just really hard to explain something that you don't understand properly on your own. I mean, like my level of understanding of negamax search with alphabetical pruning. By the way, why calls negamax search? Because we are negating the score every time we're going for this recursive call. So we're using minus alpha minus beta. Here, minus beta minus alpha, sorry. So we are negating the score, and that's the reason why we use positive score for whites when returning from our evaluation, and negative score for black. So I'm really more likely to understand how the mode generator works, all these incremental updates, Zobrist hashing a little bit. Well, now I had some issues with understanding that previously, but now it's more or less just fine. So yeah, that's kind of it. But I feel really like it's not my territory, the alphabetical search. So my current understanding really kind of sucks, to be honest. So it's not really that great. But we have some search. So I think this kind of like 8 nodes, depth 8 plies dip is quite pretty okay. So I think we stick to this implementation, and now we'll be working on connecting this to the GUI. So well, first again, like just repeating myself, so I would try to connect this to WinBoard, and if it works, I will provide a detailed instruction on how you guys can do that, if for those interested. If some miracle happens and someone from Chinese guys would ask me to make sure this works with their GUIs that they use, I would first ask to share that GUI, and in case if I would be able to run the GUI in my environment, and if I wouldn't know, let's say they give me also the engine that they use in their So I would make sure what the protocol, how exactly works. In that case, I will try to fit that GUI as well. Probably that is ever on the cards. So yeah, but again, like the main goal, as I've been mentioning before, so just a little teaser for the future, probably not the next video, but definitely some upcoming videos are about to be covering that. So I'm gonna be cloning my GUI from my WukongJS, and instead of this international Western chess board, I will render the Xiangqi board, and it would be all the same. But by the way, I've changed the move notation from a standard algebraic notation to UCI notation, because otherwise it's just buggy and not really that great. So yeah, probably adding opening moves, adding this kind of like bots difficulties, literally starting from the random player and up to the actual engine's strength, whatever it is. So also this PGN writing would be on the cards. Again, like it's a little bit tricky to know whether this would be whether it would be possible to read by the GUIs or not. So we'll see, but at very least the game would be saved. It's not going to be lost for those interested to analyze your game after played versus engine. Here I would use traditional Chinese versus Romanized pieces. Flip the board would be the same, make move, undo, new game, and parse FEN and download PGN, all the same stuff. I already have a fantastic background, so the only thing needed is just to change the board, and we would be in the territory of the very first initial release of WukongJS engine, capable of playing the game of Xiangqi. This is it from my side, guys. Thanks for watching. Until the next time, and take care.